Hi there, I'm Michael Fudge, just getting ready to go for a dip in the old pool. I'm sure this lesson's going to be a big splash, so let's dive right in. Okay, let's get started with data normalization. What's on the agenda today? We'll start out with what is data normalization. Understanding the anomalies and inconsistencies in data is important to identifying how to address them with normalization. We'll define each of the normal forms, and we'll gain an understanding of how to identify the normal form that your data is in through data dependencies. Then we will go through the normalization process of improving table design by transitioning to the other normal forms. Let's start out with what is data normalization. So data normalization is basically a process that seeks to improve the design of a relational database. The normalization process consists of a series of ordered tests over each of the data in every table that you have. So it's not something you apply to one table, you apply to every table. And when a given test fails, there is a process that we use to remedy the problem and improve the design. And basically, when you normalize, you are making more tables by finding the dependencies within the data and then splitting them out into foreign key, primary key relationships. So this involves redesigning the tables and then moving data into the new versions of the table. So it would only be half the story if I taught you how to identify the problems. I have to teach you today how to identify the problems and then also remedy them. So we'll do a case study as we go about doing this. The best way to learn this is by example. So we have this example called Cuse Rides, and Cuse Rides is basically a fictitious rideshare program with fixed rates. I know it sounds great, but it's fake. And basically the pricing model is there are drivers and vehicles, and Cuse Rides owns a bunch of vehicles, and drivers agree to work for Cuse Rides. And then the fee we charge people is based on the driver and the vehicle, and that ends up being the fixed rate. Before any driver can use a vehicle, they must pass a certification exam that demonstrates on the road that they are capable of driving that vehicle. And then the pricing model, as I said before, is if the driver charges $10 an hour and the vehicle costs $15 or $10 a trip, and the vehicle costs $15 a trip, then the whole trip is going to be $25. So here's our case study, Cuse Rides, and this is a table. And the database is a very bad design. All of the data is in one table. Imagine they started this application using a spreadsheet, just keeping track of people like this person, Bill Me Later, and then Bill Me Later got a 90 on the exam to drive this Nissan Leaf, and that's the date. And then later, Bill Me Later, got a certification exam. He got a 78 on it for this Chevy Trax. And the Chevy Trax has some things in it, like it has a USB place where you can plug in your phone, and it has Bluetooth. The Nissan Leaf has USB port and audio, or XM radio, I mean. And likewise, each of these drivers will drive in a certain area of the city. So Willie Drive will drive in the south side and downtown, and Caroling will drive in the south side and the west side. So each of these, if you want to go to the west side, then, you're obviously not going to use sail to boat because sail says north and downtown. So you see there's a lot of data here and a lot of data dependencies and a lot of interdependencies. This design was not well thought out. When we learned in the beginning of the course how to build a database from a conceptual model, we said look at the entities, right? And so you might say, well, driver's one entity and car's another entity, and taking the test is another entity, and et cetera, et cetera, et cetera. But obviously the person that designed this database did not think that way, and they took a very different approach. And most of the time when you're normalizing, you are correcting an existing model. Okay, you're taking a look at a model that is there but not working and trying to find a way to make it work. So how does normalization improve the database design? It does it through two things. The process of normalization will identify hidden dependencies in the data, which might have been overlooked throughout the design process. You just didn't think about it as you were doing the design process. And those dependencies reveal themselves through inconsistencies in our data, which are derived from these internal data anomalies. Okay, and a data anomaly is you go to perform a DML operation, but the DML operation doesn't work the way you would expect it to, and therefore it creates inconsistent data. So what do we mean by inconsistent data? Well, let's go back to the original example that I just showed you, and let's look at this. Well, this person here sailed the boat. That's the same person, but his name is spelled incorrectly the last time, or maybe it was spelled incorrectly the first two times. We don't know, right? Problem is Sale should only be in this database once, but he's in here 3 times. Likewise, this car, this Nissan Leaf or this Nissan Leaf, depending on which row you look at, it's really the same car. It's got the same license plate, it's the same vehicle size, make, and model. So why is it in here 3 times if it's the same car, right? This doesn't necessarily imply you're going to have data inconsistencies, but it will definitely yield data inconsistencies. And then likewise, when I go to find out, where the downtown, who drives downtown, do I look in the region 1 column, the region 2 column, the region 3 column? Do I need to look at all 3? This is why this database is not very consistent. Okay, so data inconsistencies yield data anomalies. And so there are 3 kinds of anomalies. There's the update anomaly, the delete anomaly, and the insert anomaly. And these generally come into play because your table isn't dry. You repeated yourself when you designed your table. You allowed multiple rows to mean the same thing. And we said in the beginning of class, 1 row refers to one thing. And we don't want to have a situation where there's 4 bill me laters and they all refer to the same bill me later. Okay, that's not good. So here's why it's not good. Let's suppose bill me later says, I want to make $10 an hour now, or I'm walking, I'm going to do Uber, right? So I have to go into a user interface, find bill me later, and then update him, right? But really, I got to update him 4 times because he's in there 4 different times, right? You know that a Power App is going to look at this, or any other app we build, is going to look at this at a row level. So you're going to open up the table and see, this row, this row, this row, this row, and Bill's going to be in there 4 times, and I got to update him 4 times. That's not good. Look at this delete anomaly. A delete anomaly occurs when you want to remove data, but the process isn't, the SQL delete statement. So when I want to remove let's suppose a Nissan Leaf needs to go in for replacement batteries, and it's going to be not available for like a month. I might want to delete it out of the fleet so that no one tries to take it for a ride because it's not there. I can't do that with this database because if I want to delete the Leaf, I have to delete it here, here, and here. And the reason the Leaf is there is because it's associated with those people. So not only do I have to delete the Leaf 3 times, but I don't even delete the record. It just has to do an SQL update to get rid of that record. So that's a big disconnect. We want SQL, when I want something deleted, I want to use the delete statement. When I want something updated, I'll use the update statement. Same thing with an insert anomaly. How do you add a person to this database? You can't unless they also are taking a test, right? So you can't hire a new person and then say, how many, it probably hasn't happened to you, but it's happened to me plenty. I'm sorry, I can't add you to the system yet because you need to do this before I can add you. That tells me that the system was designed with some kind of anomaly in it, and that it is a poor design, and it really is a good candidate to be normalized, and so that design can be corrected. So in this particular case, this person Ida No, we couldn't even add Ida No unless we also knew that Ida was going to take that test for that Nissan Leaf, or any car for that matter. And that ends up being a problem. All right, so what's next? We have some data redundancy. that data redundancy leads to inconsistency, and then those anomalies create redundancies, and those redundancies lead to inconsistencies. This is caused by poor design, right? So how do we fix it? One way you can fix it is you can go back, put your analyst hat on, look at what we did in the QS application, and then say, let's start from scratch. All right, so what's a business process here? Well, we've got customers, and we have cars, and we have drivers, and before those, there's a rule that says that the driver has to pass an exam before they can drive the car, and then put your one-to-manys together, right, and build your relationships, and then map that and get the tables you want. Okay, there's another way to do this where it's too late for that. You already have data, and you just want to improve the data you have. This is called normalizing. And when we normalize, we identify the data dependencies, and we resolve them. So the key step in normalization is to understand the data dependencies. And this is a fairly trivial process. It requires a little attention to detail, but it's not something that is beyond anyone's grasp. So data dependencies define the relationship between the attributes in a table. And basically what you're doing is you're looking at two columns and comparing them to each other. And between two columns, A and B, one column may not be usable by the key. So if A is the key, column B cannot be used, or column A cannot be used to find a value from column B. Sometimes a column acts as the key. Sometimes a column is the key or part of a key. So those are basically all the different roles that you might have in terms of potentially problematic data dependencies. So let's look at the simplest dependency, that is a key dependency. So a key dependency exists between column A and B when column A can be used to look up a single value in column B. I know it says no key dependency there, but it really should say key dependency. That's a mistake. So, for example, with our driver ID as the key, right? Anytime you see 101, you get a single value over here. Okay, and so that means that we can use driver ID to find the driver fee. Now you might say, well, isn't the reverse true? Well, the reverse is not true, because you could have the driver fee 1250 is 102, but it also is 104, right? So in this case, driver ID acts as a key and allows us to look up the values in the driver fee column. So we say that driver fee has a key dependency on driver ID. Okay. So here's no key dependency. A no key dependency means that you cannot use the key to find the value in the other column. So there exists a no key dependency exists between columns A and B when column A is a key and cannot be used to look up a single atomic value from column B. I can use column A to get this USB port, XM radio, but I cannot use column A to just get XM radio or just get USB port. So in this example, license plate cannot be used to look up a single feature, that is, one value. And that's because car features is conceptually multi-valued. It's a multi-valued attribute, and the way that this person decided to implement in the database was just with a bunch of commas in a field. Okay. So while the same license plate looks up the same features, you cannot select a single atomic feature from XM radio, not without using a pivot or some kind of really complicated query logic that we may not want to get involved in implementing at that particular juncture. So let's talk partial key dependencies now. We talked about key dependencies and no key dependency. Now let's talk about partial key dependencies. Partial key dependencies are only in a situation where you have a composite key, that is, a key that is made up of more than one column. And in a partial key dependency, only one of the columns in the key is required to act as key for the other non-key column. And I know that was a lot, and I said it a lot, but let me use an example. So we have driver ID and license plate, but really we do not need license plate to find the driver's name. The license plate is part of the key, but not necessary to figure out which driver is which. For example, driver 102 is always Willie Drive. It doesn't matter what the license plate is. Driver 104 is always Carol Ing. It doesn't matter what the license plate is. This is called a partial dependency because driver name only requires the driver ID to be looked up. It doesn't require that license plate. Okay. You only have to worry about partial dependencies when you have a key with 2 or 3 columns in it. And then the other column is obviously a non-key value. So finally, we get to the most sophisticated of the dependencies, the transitive dependency. And a transitive dependency exists. You notice how the word key is not in here anymore because a transitive dependency doesn't have anything to do with a key. A transitive dependency exists between column A and B when column A is not a key, but it can be used to look up a single atomic value in column B. So neither column A nor B are keys, but one of them acts like a key. One of them behaves like a key. So in this example, we have license plate as the key, but actually the size of the car can be used as a key to figure out how much we charge for that car. So whenever you see small, it's always $7.50. Whenever you see large, it's $12.50. And whenever you see medium, it's $10. So in essence, car size is acting as a key for car fee, and therefore it is a transitive dependency. We call it transitive because the way you get to car fee is you go from license plate and then use car size, and then from car size you can in turn use car fee. Okay. All right. We got our key dependencies, our non-key dependencies, our partial key dependencies, and our transitive key dependencies out of the way. So now it's time to really focus in, really hone in on these normal forms. A normal form is a representation of the state of the data, okay, with respect to dependencies. It is a check that you put on the data within the table and you say, does it pass this dependency or does it have this dependency? And based on that, you label the data as a certain normal form. So these are just definitions, and there's 4 definitions, and I want to reiterate, they're just definitions. Okay, there's no magic here. Zero normal form means that your table has at least one column with no key dependency in it. Okay? So the hard part of knowing this is what is a no key dependency, right? No key dependency means whatever you have chosen as key can't be used to look up that column because there's more than one value in it, right? So if that happens, the table is in zero normal form. First normal form has no columns in it with a no key dependency. So every single column is key dependent. Second normal form must satisfy first normal form. That is, there should be no key dependencies. There should be 0 columns with no key dependencies. And then also, there should be 0 columns with partial dependencies. So it's a stacking thing. Not only is it no key dependency, but also partial dependency. And then obviously third normal form is all 3. You have no key dependency, you have partial key dependency, and you have no transitive dependencies. You have no all the way across the board. It's like grandma talking to me when I was little. No. So let's think about this visually then. So if you have a bullseye, the center of the bullseye is third normal form because it's the strictest of rules that requires all the other rules, right? So this is 0 normal form, first normal form, second normal form, third normal form. And you get all the way into that bullseye, you have to pass through the other normal forms. Okay, so if you start out in 0 normal form, you must get rid of the no key dependencies. What does get rid of them mean? It means take them and put them in another table and then redesign that table so that there's no key dependency in there. And usually there's going to be a primary forward key relationship back to the original table. And then poof, now you have no data anomalies anymore. So you resolve the no key dependencies. Then you're in first normal form. Then you resolve the partial key dependencies. Then you're in second normal form. Then you resolve the transitive dependencies. And poof, you're in third normal form. Okay, here's where we're going to spend the meat of the rest of the unit, diving deep into the normalization process. We will, by example, show you how to detect all of the different dependencies and then resolve the dependencies, both through new tables and by moving the data into those new tables. So this flowchart outlines the basic process of performing the normalization going all the way to third normal form by selecting a key, then testing through all of your different dependencies. The example we will do will need resolutions at all three levels. In life, there's not always a resolution that has to be done at every single level. Sometimes you don't have any non-key dependencies, but you have a partial key dependency, and then you don't have any transitive dependencies, and then you're done. Sometimes you have no non-key dependencies and you don't have any partial key dependencies, but you only have a transitive dependency. So you resolve that and then you're done. But in this example, we're going to have to do all three steps. That's by design. That's on purpose so that we can see how this works. As a result, it's going to be a pretty complicated normalization, but it's sort of good to know. So you're going to see this slide a lot, as you'll see right now. Right now we're in this step, key selection, and we're going to work through all 7 steps and all 3 normal forms on the way to ending the unit. So key selection. For each table to be normalized, there must be a selected key from the data. This key cannot be a surrogate key. Surrogate keys are not going to work because, again, they're system generated. They have no meaning within context to the other keys. So therefore, there's no legitimate data dependency from a surrogate key. You should use a natural or business key. If there is no natural or business key, then you should select the minimal candidate key from the data provided. So let's do an example. In this example, for Cuse rides, we're going to select driver ID and license plate together. So why are those chosen? Well, number one, in the original table that I got this data from, that was the primary key. Number two, it makes sense because one row means somebody took a test. What does it mean to take a test? It means, Bill got in a car, Bill got in the Nissan Leaf, and he drove the road test, and he scored a 90. Sailed the boat, got in the Chevy Trax on April 2nd, and it got an 85 on his test. So it's the combination of driver, vehicle, when they took the test, and the score they got. Okay? Now that we have selected a key, we can answer the first question. Are all columns dependent on that key? So identifying no key dependencies. No key dependencies are multi-valued attributes in disguise. Basically, conceptually, someone took a multi-valued attribute and just left it in there in the table and then said, whatever, I'll figure out how to deal with it later, and then never did. And so as a result, you have a hidden many-to-many relationship that's shoved into one attribute. Okay. In both cases, the data is not queryable in the current format. So it's impossible to answer basic questions when you have several atomic values in a single field. Not without using some technique like using unpivot or string split or something like that. So again, from that data modeling perspective, this is the equivalent of an M attribute that was just kind of left for dead and never addressed. So here's an example from Cuse rides, and I've subsetted the Cuse rides table so that we can just focus on what's important. And I'll do this in each of these examples so that it makes more sense to us what we need to emphasize. So in here, you'll see I have two columns for the key, as they always were, and then I have these columns here. So the fleet table has two no-key dependencies. The first one is this regions area here, because what they've done here is they've said, all right, one driver, many regions, here's the three regions, each are in a different column. Likewise, there's another one over here with how the car is equipped. So this particular car is equipped with a Bluetooth, audio, navigation, and a USB port. That's three different car features for that one vehicle. So how do we go about fixing this? This is the big thing. How do we go about correcting this kind of problem? Well, you're going to see these diagrams a lot, so I'm going to spend a little bit of time explaining it right now, because you're going to see them a lot more. So the solid table represents the table we already had, okay? And the dashed tables represent the new tables that get generated through the resolution of the key dependency. So in the no key situation, it was a hidden many-to-many. So we have within an attribute. So we have a bridge table and then a lookup table, right? So over here are going to be, for example, all of the different regions: downtown, west side, south side, north side. And then in here is going to be the combination of primary key from the original table and then west side, south side, downtown, so that we can then hook it back up with the driver's car. Okay. Again, many-to-many relationships hidden inside a column. We need to add a lookup table and a bridge table. Lookup tables hold multiple values. Bridge table sustains the original relationship to the key. Okay. No key dependencies are moved to the bridge table. Unique values go in the lookup table. So here's a visual example of that. And then after this, we'll probably do a demo where we write some code. So here's the original table. Let's just look at regions first. These are the no key values, right? They don't satisfy this key. So that's why they're X'd. They're going to end up in another table. So we create there's the original table. And now here comes the dash table, right? This table has all the unique regions in it: downtown, east, west, north, south. Then in the middle, we have a bridge table. And that bridge table consists of the primary key of the original table plus this key as a foreign key back to the lookup table. All three of these columns together are the primary key. Now later on, we're going to see that you don't need, let me get my fat hat out of the way. Later on, you're going to see that you don't need all three of these columns, but that's actually another check. That's the partial dependency check. That's not this check. Okay, this check is different. So you see what happens here. We used to have, south downtown, like 102 south downtown. Now I got 102 downtown, 102 south. Now why is it in here twice? Two different license plates. Okay, but you can see that this is only dependent on the driver ID, but we'll cover that again in a bit. It's important you follow these in the right order. So here's how you resolve this type of attribute. Very similar, right? So in this case, car features comes out. The original table looks like this again. We have a car feature table like this over here with just the unique values of all the possible features. And then in the middle, we have a bridge table. And that bridge table, again, has the driver's ID and license plate as one key, and then the car feature as the other key. Okay. So it's demo time. And in this demo, we will use the CR Fleet table in the demo database, and we will end up making these tables to put our data in, and then we will migrate our data accordingly. And there's going to be some various techniques that you're going to see along the way, and what you'll notice when you're doing this is that there is a pattern that you follow to do this, and it's a pretty common pattern. Okay, so without further ado, let's get into it. Now, the first example in each of these, I will go into the gory detail of doing it all. In the second ones, I'll give you the code and just sort of explain the code. That way, you don't sit there and watch me type for hours. There's a lot of code in this. When you're all done, you can have the code. That's fine. But you certainly don't want to watch me type 200 lines of SQL code to migrate this beast over. Okay? Okay, I'm out here in Azure Data Studio, and I have run a query on that fleet table showing you everything. And the columns in question are these region columns, right? And this features column. Those need to be removed from the table. So the first thing we might want to think of is what does this table, this fleet table, look like with those columns removed? And that's actually very easy to do. So this would be CR fleet after first normal form. So I like to do this when I normalize. What I like to do is I'll take the database, get it offline somewhere, and because this is an arduous process, especially when it needs serious normalization. And then when I finally get it the way I want, I can then generate the right tables that I need. But as I go along the way, I'm going to be making a lot of tables because I don't know how far I'm going to have to dissect this table to get it to be right. So in essence, what I'm doing is this is how I get to first normal form with this table. Okay. So it would be select CR fleet, but I don't want any of the regions in there, right? So I need to say driver ID, driver name, driver fee. Skip the regions because those are going to end up in a new table. License plate, make, model, car size, car fee. Car features, they end up in another table. Test date, test score. And I forgot a comma. Won't be my first, won't be my last. Okay, this is going to be a table that satisfies first normal form. Why? Because if I look at this key and this as key, those all retrieve one value back at the intersection of row and column. I don't have multiple values in there anymore. So this table would be in first normal form. Excellent. So let's do another one. How do I make a table? How do I put this in a table? We'll do that in a second. Okay. The next challenge that we want to address is how do I get just the names of all of these different fleets, right? So let's go back and let all of those different regions. How do I make a table out of this that just has a single column with unique regions in it? Well, you might remember back earlier in the class, we learned about how to do a union query, right? And one way to combine 3 columns into one is use a union. So if I take region 1 and you select that, union select that to region 2, and then union select that to region 3. Let's see what we get. Okay, closer, right? Now I get 1 for each, but I still have null in there. So what I have to do is just make sure I filter out null, where region 1 is not null. And region 2 is not null. And where region 3 is not null. Let's see how that looks. That's pretty good. I want to make a table out of that. Actually, I don't want to call it region 1. I want to call it region. So I'm just going to alias this one as region. Remember, if you alias the first one, that's what ends up being the output. You know, this is the reason that this unit is last, by the way, is it really does culminate all the knowledge you learned in the class. You got to know about modeling. You got to know about logical models, primary keys, foreign keys, one-to-manys, all that stuff. You got to know the SQL. Okay, you're going to see the union, you're going to see string split, you're going to see unpivot, you're going to see it all. Okay, you're going to see alter table. To do a migration, to do normalization, it takes every bit of skill you learned in the class. Okay, so that one does the fleet, this one does the region. So this is probably like the CR region table. Let's do that bridge table now. Now remember that bridge table consists of the driver ID, and then the license plate, and then the region. Something like this. Right? But this isn't accurate because I need every region. And I want to make sure those regions are associated with the right driver and license plate. So this bridge table is going to be CR fleet regions. And let's think this one through. It's going to be select select this from CR fleet pivot, and I want to pivot region for, I want to unpivot, not pivot, region for region column in region 1, region 2, region 3. Now there's a couple ways you could do this, but this one seems to make the most sense to me as unpivot. Okay, I forgot to include these columns over here, region. Watch this, I'll include region, column, and region, because you might have forgot how to do an unpivot. Let me just kind of make this look a little sexier. There. Okay, so I have like, this one is region 1 column west, region 2 column north, region 3 column downtown. Okay, so now I don't need to show this column. It's not necessary. It doesn't need to be part of what I'm trying to accomplish here. So I can just get rid of this region column. Okay, so I've shaped my data, but this isn't good because I need to put these in tables. I can't just write select queries. I need to take this data and put it in a table that I've made that has these columns in it, right? Because when you normalize, you're making new tables. As you saw in the PowerPoints, there was the original table, the bridge table, and then the lookup table, right? So I have the original table, the lookup table, and the bridge table. And how do I get them into a table? Well, the pattern to get them into the table is always the same. So there is a command that you can add to the select statement called into. And what this will do is drop the query into a target table. It creates the table when you run it. So in this case, I'm going to call this CR fleet 1NF. That's the table I want to make. When I run this query, I don't see anything. But if I go look at my database, now I've got another table. And this table, if I select from it, it looks like the query, but now the data is stored in the table. So this is the pattern you want to use when normalizing. When do you add 1NF at the end? Only when you're taking an existing table and normalizing that table, right? These ones are new tables, so this one will just be called CR region. It won't be called CR region 1NF. There's no need. Okay, so if I do this and run it, it's not up-down friendly. It says there's already an object named that, so I need to make this up-down friendly. Drop table if exists. Because you want to be able to run this whole darn thing, right? This whole normalization script. CR fleet 1NF. Oh, this should be CR Fleet 1NF here. I'm sorry. Let's try that. Put a go in here. Okay, that's better. Now there's one last thing that you must do. Unless you're in the business of visually verifying that you have entity integrity, you will want to, and you're not, you need to set a primary key here on this table, on the CR Fleet 1NF table, so that you can guarantee that you have entity integrity. And that entity integrity is important because with that entity integrity, you know that you haven't duplicated what you have said through the normalization process is the key, right? Which is this and this. Whether or not we actually use them as primary key when we get all done, that's up to us. We could go ahead and use surrogate keys if we want. We don't have to use license plate. We can use license plate ID or whatever. But while you're normalizing, you have to continue to use the business keys, the natural keys, or some combination of minimal surrogate key. You just have to. So with that in mind, let's add our key back. So I'm going to alter table CR Fleet 1NF, and then we're going to add a constraint, and we're going to call it PK CR Fleet 1NF, and it's going to be a primary key constraint on driver ID and license plate, right? It was a composite key. So if this works, then this migration was right because I still preserve the entity integrity that I had before. If it's not, then I need to look at what I did because something isn't right here. A row repeats that shouldn't. Okay? So this is a fantastic check to make sure that you are migrating that table correctly. And it works. Beautiful. Okay. So now we have a strategy, and we must rinse, lather, and repeat that strategy for each table in the migration. So this is the next thing I want to migrate. Right? So I need to insert this into a table. Now, this is a composite select statement, so I have to use with here. I have to say with. See, I told you you're going to use everything in the playbook. This is why I teach it last, because you can teach normalization without migrating the data, but what's the point? You got to know how to move that. You got to know how to fix it. If you see a problem, you got to know how to fix it. And you can't fix it unless you know how to use SQL to programmatically move data around. So now I can say select into, and then this would be CR region from source. And then that's going to insert this into a table called CR region. Let me do that. And if I go over here and look, there's a CR region now. And if I just take a look at it, there's a date in it. The problem is there's no primary key set on it. Okay? So we got to make it up-down friendly, right? So drop table if exists CR region. Oh, I should probably get that in the copy-paste buffer, right? Let's do this. Drop it if it exists. Go. This. Okay, so this is, drop if exists. This is this is called a make table query, which makes a table, create table from select. And then after that, we need to make sure that we deal with the primary key, right? So the primary key of this table is just going to be region. There's only one column in the table. So we need to say it's right here, right? But it's not a primary key. See, there's no key. Got to make one. So, I alter table CR region, add constraint, PK region, primary. The only reason I'm showing you this is it's going to error out, and I want you to see the error. At this point, it's close to boilerplate, but I want you to see it. Oop, I got this wrong. I took this. This goes here. Yeah, that looks better. And then I need to have my select My verification is select star from region. CR region. Okay. All right, let's see what happens here. Okay, and I get this problem. Primary key constraint is on nullable column. When you use the make table syntax, it will only put not null on the current primary keys. So if you look, it says it allows null. That's not what we want. So I need to alter the table and fix that. Before I set the primary key, I must alter the region table and alter the column region. It's going to be varchar 20, not null. Right now it allows null. That's how you fix that. Okay. And now this should all work. And it does. Okay. Okay, a little bit of fast forwarding magic here, and I have the scripts for the rest of them. They're all kind of the same boilerplate. The thing that you want to really emphasize is how did I go about getting those unique car features? They're all in individual columns, right? So I use the string split with a cross apply to take them out of their comma delimited column and put them in their own row, one per row, right? So that one does that, and then when I do the bridge table, I do not use a distinct. I just show them all, right, with the driver's name and the license plate. I got to take the into out so you can see it. So see, I needed a cross apply for this one, right? And again, why is it a cross apply? If I would just go down to the bottom here and do a select star from CR fleet, you'll see that it is comma delimited over here in car features. So when I have I want to get the car features out, I have to say, you know, cross apply string split those car features on a comma. And then with that, I wanted to include, you know, I think it was driver ID and license plate. Right, so you can see every trick in the book is needed to make this baby go. And I forgot to include value here. Every trick in the book is needed to make this sucker go. And, you know, that is why it's so challenging to normalize. Now, I will say this. The first normal form is by far the hardest. Okay, now our data is in first normal form. Awesome. What does that mean? Well, it means that we resolved any of the no key dependencies. So originally, we had just fleet up at the top, but now we've got these two extra tables that we added. This one establishes the regions relationship, and this one establishes the features relationship. And you saw in that code, I made up-down scripts for all 5 of these tables. I had to restructure this table to remove the columns that don't belong there anymore. And then I had to make these 4 tables here, 2 lookup tables, 2 bridge tables. Okay, and now it's in first normal form. That's a lot. That's our most complicated one, and it's the most complicated one. Number one, because there's 2 of them, and number 2, because when you're dealing with data that is not in first normal form, you always have to make 2 tables. So it's pretty sophisticated. But you did see 2 very common techniques you use. In the multi-column instance, where you have region 1, region 2, region 3, we use select with union. In the comma delimited single column scenario, we used string split with cross apply. These are common techniques you can use to address your data, because it's either going to be in one format or the other. Okay, we're hunkering along now. Now we're dealing with partial dependencies. We're going to take a look at these. So partial key dependencies occur when there is a composite key and only part of the key is necessary to look up in a single atomic value. These are usually many-to-many relationships embedded within a single table. The many-to-many relationship we saw in the earlier example was embedded in a single column. This many-to-many relationship is embedded in the table, so it's much easier to resolve than in the previous example. If the table has a single column key, it can't have a partial dependency, so there's no real need to address this problem. If a table does not have any non-key columns, it cannot have a partial dependency. Okay. So let's take a look at QSrides again. Let's identify the partial dependencies. Again, I've removed the irrelevant columns so that we can just focus on what's important here. And you'll see I have this red key over here and this blue key over here. They're both primary key. They're both set as the key for doing normalization within this data set. Let's see where this takes us with a partial key. So the fleet has two partial key dependencies. I hope you see them. See, only the driver ID is necessary to look up a name or fee for that driver. I don't need the license plate to find the driver fee. I can use the driver. 101, it's always $7.50. 103, it's always $10. 103 is always sailed a boat. So these two columns only need driver ID. Likewise, a license plate is needed to only look up make, model, car size, and car fee. Right? Because whenever I see this license plate, it's a Nissan Leaf, small, $750. Whenever I see this license plate, it's Chevy Trax, small, $750. Now these two columns over here, they need both values in the key. Okay, this value here, test date, depends on the car and the driver. This score here depends on the car and the driver. So these will remain in the table. Everything else going in two new tables, as you could probably sniff it out by now. So how do we go about resolving those partial key dependencies into new tables? Here we go. So in the center, you have your original table. And then each of the partial dependencies go into one table. And then the other partial dependencies go into the other. If you only have partial dependencies with one side, you're only going to make one table. That's okay. But in this case, we have partial dependencies with both keys. So we will introduce two new tables. So in essence, this is not going to make more rows in the table. It's going to make less as we take the original table and reduce the rows. See, it goes primary key, foreign key. So one to many here. So this table, the original table was the many in the many-to-many relationship. It's like someone took a many-to-many relationship, joined it, and shoved everything together. Partially dependent non-key values are removed from the original table and added to the new tables. Primary keys in the new table is the part of the key which the columns were dependent upon. So in this case, the driver ID for one or the license plate for the other. The original table is now an associative entity when you think about it, because what you're saying is, driver permitted to drive vehicle permitted to be driven by driver, many to many. Oh, it's got data, make an associative entity. So usually this happens when the designer doesn't understand associative entities and then just shoves everything into one big table. That's usually when you see a situation like this. So getting into the nitty gritty in the columns, here's what it looks like. The red X's go with the red key. The blue X's go with the blue key. So these things here are going to end up in their own new table. These things here are going to end up in their own new table. What stays in the original table? This key, that key, and these other two columns. So there you go. Original table, driver ID, license plate, the two columns. One of the new tables, you can almost envision it. It's going to be only the unique driver IDs, because now this becomes primary key. And then only unique instances of name and fee. So you have your one-to-many here, right? One driver, many tests for cars. And then likewise the other way, one car, many drivers who took that test. Right? So we have taken a many-to-many that was like joined together, and we have now unjoined that many-to-many into three tables. The original table plus two new ones. Okay. So there's one more thing to think about, and that is when we did our first normal form and made those bridge tables, we now can go back and resolve the partial dependencies that exist within those tables. For example, now that we have a separate drivers table, we can address the fact that this license plate here is not necessary to determine the driver's region, right? If you look back here, driver 101 downtown, the reason it's here 3 times is because it's 3 different cars. But the car has no dependency on the region. The region can be derived just from the driver's ID. Okay, we don't need the license plate to do that. So when we remove this, we can reduce the rows in this table considerably because these 3 rows will go down to 1 row. Likewise, we could do the same thing with the car features because the car features don't have anything to do with the driver. They just have to do with the car. So this is one of the issues with partial dependencies is that you need to go back and check the rules you did in first normal form. Make sure you didn't miss anything that might apply to the second normal form case. Okay, it's time to go back to the demo. And now in this example, we will create those drivers and vehicles tables. I will show you how to use select distinct to perform your row reduction. And then we will also remove the redundant key from fleet and drivers. Okay, you can almost see how this is going to play out. Maybe, I don't know, maybe not. So I have our first normal form fleet table, right? And now what I need to do is get rid of everything that was partially dependent. So that would be this column, that column, that column, that column, that column, that column. And then that is going to be the fleet table in second normal form. It shouldn't have any of those columns in it. They're all going to go into new tables, right? So it's pretty easy to make this query to satisfy this. We would have driver ID. So this one, by the way, is going to be, if we name this, it's going to be CR fleet second normal form. Select driver ID, driver name, driver fee, license plate. Oh, I don't want driver name and driver fee. Those are partially dependent. So I want driver ID, license plate, test date, and test score. Those are the only things that should remain in this table. So that's going to look like this. All right. So that's one table. And we know how to do all this stuff to make it work. So we'll skip that for now. And then we're going to do CR drivers. And this is going to be select driver ID, CR fleet 1NF, driver ID, driver name, driver fee. Okay, a lot of repetition here. We want this to actually act as a key. So one way to get rid of all this repetition is use distinct. Right? Give me only unique values. And there you go. Now you just have the 5 drivers. See, now this is much easier to maintain entity integrity, number 1. And number 2, deal with any kinds of anomalies. Because if Willie Drive changes his name to Willie Survive, then I just need to change it in one place. Just change it in one place. Right? I don't have to change it in 3 places. And an update's an update. Bill me later leaves, I delete bill me later. There we go. Okay. Let's do vehicles. I'll go for the home run. License plate, make, model, car, size, car fee. There we go. So I've got my 3 tables. Now I just have to surround them with, I have to change this to an into, right? And then give it a table name, CR vehicles. And then I need to drop it and then make sure I set a primary key. Okay, so pause video while I do that. Okay, and through the magic of movie pausing, I was able to create my drop for my fleet, and then I make my fleet. Then I add the primary key constraint, and then make sure it works. Then I drop drivers, create drivers, add the make sure it's not null on the driver ID, and set that primary key. Then I do the same for car. Okay, then down here I had to deal with, I had fleet regions, and I had fleet regions and I had fleet features, and I had to fix that. So what I did here was I just grabbed from fleet regions, I just grabbed driver ID and region and select distinct it, right? So let me show you this. If I turn off into really quickly and just show you a select from this, you know, I get a lot of rows and they're redundant. 101 downtown, 101 downtown again, right? So in order to fix this, I put distinct in here. You can see there's, I don't know, 32 rows. And now there is 11 rows because there are just 11 unique combinations of driver and region. So this greatly simplifies the amount of data in that table because I removed the dependency on license plate that wasn't necessary. It wasn't even necessary. So now this table is actually going to end up joining up with the driver table and not the original fleet table. Okay, so I did that, and I did the same thing for regions. Let me run the whole thing, make sure it works. Boom, look at that. Everything ran. Awesome. Oh, there's a couple errors. What do I got going on here? Fleet features. Did I not call it fleet features? Yeah, it seems like I commented it out to show you something and then never uncommented it. So that was the problem. All right, so that worked. Everything went in okay. And then I go over to tables. And now I have a bunch of tables here. And you might be wondering, like, which ones do I use and stuff? Well, I'll talk about that after we get through third normal form. So where are we now? Let's go find out. So here we are. We're in second normal form now. And when we live in second normal form, now we got a heap and help in the tables, right? We have taken the fleet table and now broken it up into two additional tables because the fleet had a hidden many-to-many relationship, and now we've broken out. So here's many, and there's one driver, and then one vehicle, right? So one vehicle, many vehicles in the fleet, one driver, many drivers in the fleet. Any one row in here corresponds to one driver. Any one row here corresponds to one vehicle. Likewise, we simplified driver regions and vehicle features so that the driver 101 just has the four values original to their region, and then same thing over here with vehicles. Okay? So that gets us into second normal form. And now we have to address the last elephant in the room, and that's the transitive dependencies. Transitive dependencies are a little sneakier to find because you have to look for non-key columns acting as key with another non-key column. So there can be quite a few permutations for you to look over when trying to identify a transitive dependency. And usually the best way to do this is to look for the obvious. You will see a lot of data repeating in a table that's already in second normal form. And you'll say to yourself, why is there still more repeating data in here? I thought I just took care of this. And that's a great indicator that what you have in front of you is a one-to-many relationship embedded within the table. So there's still a one-to-many relationship hidden somewhere in your table that you have to resolve. So to identify the transitive dependencies, we must focus on the non-key columns within the table. Table requires at least two non-key columns to exist for a transitive dependency to exist. And there is a transitive dependency in the vehicles table here. This is a screenshot of part of the vehicles table, just a little bit of it. And you can see that we have the vehicles table has a license plate key. And the car size and car fee have a transitive dependency here because the fee really depends on the size of the car, not the license plate. Okay, it's not directly dependent on the license plate. You can have two different cars, Leaf and Trax. Their fees are the same because they're both the same size. That's just the business model they chose. There's actually a hidden table in here. You can take this stuff and make a smaller table out of it and then join it back to the original table. It's transitive because car fee does not require the license plate directly. It really just depends on the car size. Okay, how do you go about resolving this? I'm going to give you a hint. More tables. Okay, the nice thing about third normal form is it only makes a single new table. It does not make two tables, thank heavens. The original table is the foreign key side, and then the transitively dependent table becomes the one side. So it's really a hidden many to one table, not a hidden one to many table. Transitively dependent values are removed from the current table, just like they always are. You remove the dependencies from the table, add them to a new table. Primary key of the new table is the column, and they are transitively dependent upon, acting as the key. And the original table's column is now the foreign key referencing the new table. So here we are in Cuse rides. This is the vehicles table. This X is what's going to be leaving the table. So when I remove this from the table, I trivially get this, which is my original table. And then what goes into the new table is a table with primary key car size and just the three different car sizes. And then that is our last resolution that we need to do. So let's take a look at this. We'll resolve the transitive dependencies in this one. Here we are back in Azure Data Studio, and I have already run the select statement to show you what the vehicles table looks like. So we're going to have to remove this car fee from this table to put it in third normal form because this car fee is the transitive dependency. That's really easy to do. So this one is going to make a table called CR vehicles 3NF because we're putting it in third normal form. It's already in second normal form. And we will do a select make model car size from CR vehicles. Ooh, a little rusty with the E's there. And there you go. That is going to be our target table. So I can, put it in my target table with my into, right? Into CR vehicles. Then I would have to add my gratuitous drop table, create table, right? Dorp. Right, and then go. There we go. Let's see if I can get this thing to actually work. Okay. CR vehicles. I got something going on here. Oh, I can't put it from and to. I got to say into CR vehicles from. It's not from. Oh, into CR vehicles 3NF. Gee, Mike. Did I just drop the table? I probably did. Yeah, I did. All right, hold on. I got to run all this code here. I don't remember where it is. I'm just going to run it all. That's the beauty of having an up-down script is you screw it up. Boom. Let's go back and do it again. And now I think I've got this right. There we go. And then my select. I also have to do the primary key, but I'll do that here. You want me to do it? I'll do it right now. Boom, done. There, how's that? There you go. Okay, now let's do the last one. So it's going to be, this is going to be a CR vehicle sizes. And this is going to follow the same pattern as the second normal form query. We're going to say select, and I'll just show you the long way. Car size, car fee from CR vehicles. It repeats, so we get rid of it with distinct. See, the only one that makes more rows is the one that fixes it and puts it in first normal form. That rule makes more rows because it has you have the one cell that turns into many. Everything else is actually a reduction of rows. It actually makes more tables, less row in each table. That's basically the way it works. Okay, so by the movie magic, there we go. And I can run them all. And now I've got a whole bunch of tables. Some of them I don't need anymore because I don't need vehicles. I need vehicles 3 and F. So that brings up a great question. And that question is, I am done. What do I do now? And the answer to that question is it depends, right? So, normally when I'm done, I'll end up making these tables the way I want their names to be, right? Because I'm not going to call the table vehicles 3 and F, right? So that might involve me now dropping some other tables that I don't need anymore. Like I don't need the original CR vehicles, right? And then I could do that and then make the table CR vehicles 3 and F, without the 3 and F on there. But for now, what I'll do is let me show you which tables we need. And I think a real fancy way to do that, I'm not going to type it, I'm going to just paste it, is to use information schema. Right? If I do this, those are the tables. Let's look them over here. So I know I need the fleet table, right? But which fleet table do I need? Well, this is the original. That's in first normal form, the second normal form, and there's no more after that. So this is actually the best fleet table that I have, right? It's actually in third normal form because I didn't have to do anything to it. I'm not going to just, rename it 3NF for the heck of it. I'm just going to do this because eventually when I go, it's going to go back to be calling CR3 fleet. I might make a new database and move them all in there or something. So what else am I going to need? Well, let's think about the drivers, right? So I'm going to need the drivers. And then I'll need the driver regions. And then I'll need the regions. All right, and then I'll need the vehicles, right? That vehicle sizes that I don't need vehicles. I want vehicles 3 and F. See, I made a mistake. Got to pick the higher one of vehicles and vehicles 3 and F. It's at the bottom of the screenshot here. So I really don't want vehicles. I want vehicles 3 and F, and I want sizes. And I want features, vehicle features, and then I just want regular features. So these are all my tables. And, they all have primary keys in them. They all have primary keys in them, but they don't have foreign keys. Like if I look at this vehicles 3 and F, and I go down here and look at the columns, there should be a foreign key on car size, and there's not. Okay, so I still have some work to do, but now that I've normalized, I can now add the foreign keys in there. You don't want to add them while you're normalizing. It's just going to make for a lot of extra typing that doesn't need to be done. So I have the code to do that. I'm going to just take that code and put it in here to sort of finish up the demo. And so I need to go into that fleet table. And I need to remember that's now a associative entity. So I need to go back and reference the driver and the vehicles tables with foreign keys. Okay, then I've got my 2 bridge tables, right? So driver regions has to reference the drivers table and the regions table. And then also I have vehicle features, and that has to reference the vehicles table and the features lookup table, right? So those are my 3 many-to-manys that got made. 2 were M attributes that were in one cell, and the other one was partial dependencies had a many-to-many within a table. And then that last one was a transitive dependency, which is just a one-to-many relationship. And so there's only one foreign key there, and that's the one that does vehicles and then adds that vehicle size to it. So this is all the code to make the foreign keys, and it works. So I've made a huge up-down script that does it all. Now I can go back over my up-down script and rename everything so that when I'm done, I don't have it called CR Fleet 2NF. I just have it called CR Fleet. And a good way to do that is don't use these names, right? So don't use down here where I have CR vehicles 3NF, right? It should be 3NF. Don't call it 3NF. Call the other one something else, and then leave the last one. Now that you know what the last one's going to be, you can go ahead and name them correctly up here in the into part. And give them the right names. Give them the target names. You'll just have to change the other names of the other ones. All right, now that we are in third normal form, what do we got? We got 8 tables because we just created this last one, vehicle size, and this final foreign key relationship to vehicles. Whew. So let's talk a little bit about whether or not we took this process a bit too far. I mean, we went from 1 table to 8 tables. Yikes. Yeah, the design is a heck of a lot better, and there's 0 chances of data anomalies now because 1 row means one thing. If I want a driver to take on a new region, I add it to driver regions. If I want to make a new region, I add it to regions. So new region, add region. New driver region, add driver region. Bill me later no longer wants to drive in the north. I delete that row from driver region. Everything makes sense. Yes. But should you normalize this far? Well, it's really a trade-off. You know, the higher normal forms make a more complex model, as you saw, but they introduce less chances for data anomalies. I usually shoot for third normal form in everything I do because I always can use the external data model to join tables back together and give people a more simplistic view of the data, but I know that data is going to be stored in the most efficient means possible. And that's honestly the goal of a relational database management system. That's why they exist. You know, some people say, you know, is first normal form required all the time? You know, can't I just leave a column with a couple of commas separating them? And the answer to that is, yeah, you can, but you're not going to be able to query the information, so you're probably going to end up using string split or unpivot or one of these really costly or heavy type of query operations. When we use string split in this class, it doesn't take up a lot of time, but we also have very small databases and very small data sets. Second normal form required? Yes. Okay, you are going to reduce the number of rows in your table and greatly reduce the amount of data redundancies. You're hiding a many-to-many relationship within a table. It's got to be fixed. Third normal form, I say yes. Some people say it depends. Sometimes it's okay to leave, like, you know, the zip code with the city and the state, postal codes with cities and states. That's a transitive dependency technically to an address. There's a lot of circumstances where that's okay, but major transitive dependencies like stuffing a vendor in the products table, those are no-nos. Okay, you don't want to do those kinds of things. Okay, and you probably wouldn't. You've learned enough database design where you know and understand the right way to approach solving the problem, and hopefully now that you've seen normalization, you've become an even better database modeler because you sort of get at a row level what these improvements are and what they're all about. The most important thing to remember is do not design your database or normalize your database in a vacuum. Do not follow these rules blindly. You don't follow these conceptual modeling and logical modeling and mapping rules. Or these normalization rules blindly. Let the needs of your database application dictate the design. Okay. That being said, yeah, most of my stuff's in third normal form, but I always let the database application dictate the design. If I know that certain fields are not going to be used, I might stuff a whole bunch of stuff in a text field because that works for the particulars of the application that I'm building. There's no need to make everything super hyper normalized all the time. Like I said, it really depends on what the application is doing and what it's all about. So I hate to give an answer, it depends, but unfortunately, that's my answer to you. It depends. So in summary, data normalization improves our table designs by eliminating anomalies, which can cause redundancies and inconsistencies. Normalization is a series of checks based on columns with no key dependencies, partial key dependencies, or transitive dependencies. The normalization process involves identifying and then resolving each of these types of dependencies. And remember, it's not a cure-all. The database application should be considered. How it's going to be used and how it's going to be queried should be considered.